I see your number 4. Claudia. 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 Claudia.
Why are you so nervous?
Because Claudia needs some work. Bruh. Oh, no. Did you not see who was set 4?
Alright, here's my problem.
Is this gonna be like a couple times a week thing from now on?
What I'm saying was you saw it.
Okay. So how's everybody doing? Do we have a homework due today?
No.
No.
And have you done that homework?
No.
Well, we're going to changing everything.
Problem 4, part 4.
Wait.
That's the stupidest question.
Yeah, I don't even know what that is. I hope you do. We had a discussion with the instructors and PAs. We had 17 different questions that might be asking in problem 4, part 4. Sorry about that. There will be some clarifications on the answer. So before I get into example of problems, including problem 4, part 4, the one I thought is that one, but it turns out it's not that one. But I'll get to that in a second. There will be a quiz, not this week, next week. That quiz is on logic stuff. Quiz 2. What's next week? It's 9 and 10. Something like that. And next week, logic and Boolean algebra. I don't think there's other things in it, but maybe sets make it into it. Definitely not counting. So, about counting, what do we have? Let's start from where we were last time. One rule was the product rule. And that's the easiest one. Independent choices. Out of fixed sets. Another rule was the sum rule, which later on, if we want to make it more interesting, becomes the inclusion-exclusion principle. Concern size of union of sets. That is, if I have 3 sets that have intersections, A, B, and C, how do I compute their union? I can't just say it's the size of A plus the size of B plus the size of C, because I'm counting stuff multiple times. So for an element here, I'm counting it in B and in C. I have to take it out once. I want the counts in the union. Every element is count how many times in the union? Exactly once. So I want the count of everyone to be 1. For an element here, I don't have to worry, right? I say B, I'm counting once, I'm done. For an element here, the problem is if I say B, N, A, and C, I'm counting 2 times. And for an element here, if I say A plus B plus C, how many times I'm counting that one? 3 times. So I have to fix those counts. That is the inclusion, exclusion. Of course, the inclusion, exclusion. If I want just sum rule is concerning with 3 sets that have no intersection. In that case, I could just say A plus B plus C if there's no common elements, right? So we did that one. We also have pigeonhole principle that we just did last time. I stated the statement of it, and we were at it. And we have the permutation rule. And we're gonna add the combination rule. And maybe we'll add some more. So maybe we'll add balls into these. And depending how far we want to go with counting, we can add a lot more. My plan is to add, these are all kind of elementary if you'd like to, and I have one or two that are completely, absolutely not elementary, like Catalan numbers. It doesn't fit in here. So if we get time Friday, we get to something like that, like real math combinatorics. Something that you wouldn't see until you take a course into combinatorics. Okay? This stuff is pretty much high school recap. Pigeon principle, just a quick overview first, and then I go to them one by one. This pigeon principle, I was surprised how difficult it's explained in here in the United States. I didn't grow up here. And in the book. So I have, like I said last time, a very easy understanding of pigeon principle. I'm going to state it right now. If I have x1, x2, xn, those are numbers or quantities. And their average, let's call it x bar. What's the arithmetic average of n numbers? How do I do that? Arithmetic average.
The sums of.
Sum them up, x1 plus x2 plus xn, right? Divide by n. That's their average. Then the pigeon principle says, let me write it in a way so you can see here. At least one xi is bigger than the average, and at least one, say, different one, xj, is smaller than the average. I think that's a pretty obvious thing, right? When you average a bunch of things, if you say, I average my grades and I get GPA 2.8, what does that mean? Well, at least one of your grades is more than 2.8, and one of them is less than 2.8, right? Because if you average, if all of them will be smaller, you couldn't get that average. The sum will be too small. If all of them will be higher, means the average will be higher. Another example, the average of ages in this room, it's 19. What does that mean? There's gotta be a person that's at least 19 years old. And there's got to be a person that's at most 19 years old. Why? If everybody will be strictly greater than 19, the average will be greater than 19. It couldn't possibly be 19. And if everybody will be strictly younger than 19, then the average will also be smaller than 19, right? Here's an example. My average gas bill for the year comes to $298 a month, the average. What does that mean? Somebody. My average gas bill over 12 months is $298.
There's at least 1 month where you spend more than that. There's
At least that.
At least.
And there is?
At least one where you spend less.
Right. If the average is 298, at some point I have to spend at least 298. And at some months I have to spend at most 298. Now, that's my understanding of this pigeonhole principle. How does this relate to the one in the book? That you literally have pigeons, like you have 200 pigeons, and you put them into, say, 200 pigeons into 10 cages, boxes. What does that principle says? At least one box has at least 20 pigeons. Right? That's what it says. Now, how does this, my rule, relates to that pigeon? What are those x's here? If I want to really mathematically create a map between what this statement is saying, this is a statement about real numbers. It says if you have those real numbers, that's what must happen. And this is a statement about birds in cages. What is the connection? What are those x's here?
The X is the number of pigeons in a particular box.
So x1 is
The number of pigeons in box A or something.
in box 1, and x2 is the number of pigeons in box 2. And who's n? The number of,
Box.
which is 10. And who's the average here? This. What is the sum, first of all? x1 plus x2 plus xn sums to, in this here, sums to what?
200.
200, because it's 200 pigeons total. And n is the number of boxes 10. And the average, 200 divided by 10, which is 20, is exactly this 20 in here. Right. So I always remember this rule, and there's various names: generalized pigeonhole and simple pigeonhole, and I don't even know which one's which. I only know this one worked for me all the time, never failed. So that's what I would do if I were you. I think that's the generalized one. I don't even know. The simplest one might be if you have 20 pigeons into 19 boxes. Then there is one with at least 2 pigeons. The reasons for the integers is that when people put pigeons into boxes, or students into classes, or cars into, say, parking lots, they always put integers, right? Nobody chops a pigeon or a car, right? So by saying this, which is a correct statement, what we really mean here, xi, if it's integer, xi has to be at least, everybody knows this sign here? Ceiling, right? If this is 3.5, the ceiling is 4. It's the integer that at least that, if not higher. And xj has to be at most what? The floor. So if that's 3.5, the floor of it is 3. So if in this case, I don't need to take ceiling and floors, because 200 by 10 is exactly an integer, so I get 20. But what happens if I have 202 pigeons? The average will be, if I divide by 10, 20.2. But assuming I'm not chopping off pigeons into parts, that means at least one box must contain how many pigeons? 21. Because if something is more than 20.2 and it's integer, it has to be at least 21. Right? So that's the story with the pigeonhole principle. In my education, we don't call it anything. We just call it clean thinking. Okay? We don't have a name for this rule. When I study mathematics, we just, So let me show you a few examples of problems that you might not think immediately those are like pigeonhole, principles, but they could be. So I have a listing here. Some of them I'm going to just give you an idea and leave them as exercise. So let me do here. I'll go back in a second to permutation. So pigeonhole. This is more like a recitation type of material. It's like problem solving. But just to clarify what's about, I'm going to list some problems. You have to figure out which ones are the pigeons and which ones are the boxes. And when you apply this rule, you're going to get the answer. That happens in the homework, will happen in recitation this way. Here's one. N plus 1 integers, call it A1, A2, up to An plus 1. There are 2 of them such that n divides 2 of them, call them AI and AJ, 2 of those, and divide the difference AI minus AJ. Any way you pick, you know, n could be 99, 100, 20, 50, any n. Any way you pick n plus 1 integers, there's two of them that if you make the difference, you get a multiple of n. Why is that? Anybody can give me an idea? So you can pick n equal 3, and then how many integers would have to be given? 4. Says any way you pick 4 integers, two of them have the difference a multiple of 3. Why is that? Can somebody tell me how do I apply this rule to get that answer? So let's say n equal 5. The statement becomes out of any 6 integers, there are 2 with difference multiple of 5. That's the same statement in particular for n equals 5. No, any integers whatsoever. How do I apply this rule to get that answer? Yes.
The holes would be like the mods of 3.
What?
You have 3 holes because there's 3 mods of 3.
N, because there's n. So in general, your argument is correct. If you think of mod n, how many modulo n's values can you have? When you divide integers at n, what are the possible reminders? 0, 1, 2. What's the last reminder when you divide with n possible? How many are in this set? N. Those are the boxes. Those are the things we throw in. How many integers I have?
N plus 1.
N plus 1 integers. Every integer has a reminder when I divide with n, right? So how many pigeons I have?
N plus 1.
N plus 1. How many boxes I have? N. There's got to be 2 of them in the same box. So if 2 of them have the same reminder, same box, what happens to their difference?
It's a multiple.
If 2 numbers have the same reminder modulo n, when I take the difference, what happens?
They have
Don't I get a multiple of n?
zero.
Hands up who's with me on this. If 2 of them say ai is nk plus some particular reminder r, and this aj is n times some other thing plus the same r, right? The same reminder. When I take the difference between ai minus aj, I get r goes away with r, I get n times k minus l, which is a multiple of n. So if 2 numbers have the same reminder, their difference have to be a multiple of n. And that actually works backwards too. If their difference is a multiple of n, it can only happen if they have the same reminder. Okay. Here's another one. Group of n people P1, P2, Pn with friends in the group. So to see this problem is like in Facebook. Here are the people, P1, P2, P3, Pn. And everyone has friends. Friends means connectivity. So here's this guy is friends with those 2. And Pn is only friends with this one. So edges mean friendship. Show that there are 2 people with same number of friends. Not with the same friends, with the same number of friends. Everybody in this classroom has Facebook. Some of us are friends within the class. Show that there's 2 people with the same number of friends.
There are n people, and each person can have at most n minus 1 friends. So you're putting n into n minus 1, n people in n minus 1 holes.
Right. So there's a little case where somebody has no friends, yet you have to take separately the other people. If one person has no friends, if there is another person with no friends, those are the 2 that have the same number of friends, which the number is 0. If there's only one person with no friends, I take that out and I'm looking at the other n minus 1 people and judge them. But yes, you look at what's the same number of friends could be from 1 to n minus 1. And I have n people that have to go into n minus 1 boxes, meaning 2 of them go in the same box. They have the same number of friends. Here's one that's difficult. Three. Any set of 100 n numbers there is a subset which is not empty of numbers with sum equal multiple of 100. So if I have 100 numbers, A1, A2, up to A100, pick some of them, but not empty, at least one. And you can pick a subset, means any ones of them, whose sum is a multiple of 100. It's still pigeons into boxes, but the pigeons are a little tricky. The pigeons here are not the numbers themselves, and are not all the subsets. There's some subsets. You have to construct those subsets. So let's see who figures this out by tomorrow. This was a math Olympiad problem.
Oh.
But this is not that hard. Once you figure out the pigeons, it's 3 lines. It's not hard. It's not the kind of problem that, okay, it requires, like the honors problem that I'm giving you are difficult. They're not Olympiad problems, but requires a lot of thinking, a lot of back and forth. This one, once you find the right idea, it can be solved in 5 minutes.
What level Olympiad problem is this?
Oh, I don't know. I have to check. And so I have a lot more of those pigeons problems. I'm going to get back to them once I do some examples. So how about one example here at this sum rule inclusion exclusion? These were at examples. Just to illustrate that. I don't know if we had anything in the homework with inclusion exclusion. Was there a problem with inclusion exclusion?
Yeah.
Then it's all right. So here's a quick example. So inclusion exclusion principle. Upper case, 2 uppercase initials. For example, mine would be Virgil Popley, right? How many possibilities? That's not an inclusion problem yet. This question, how many pairs of initials, it's what kind of rules I'm asking for. If I allow any initial with any initial, yes. That's product rule. So it's anything, right? The size of this is 26 letters, right? That's all the capitals letters. Times 26, that's 26 squared. How about if I say, that's part A, part B. How many that contain Z? Obviously, VP does not contain Z in it, yes.
It's now like kind of probably answerable, I guess. Because
How do I think of this question? I want all pairs of initials that contain z. So I clearly is much smaller set than all of them. Yes, let him finish. Let's see.
so only 26 things are changing now because one of them's always set as z. So
But it could be the first one could be z, or the second one could be z.
and then you add it with the possibility of the other thing. So it's 26 times 2.
So how about we think of it systematically? When you think of a counting problem, you have to find a systematic way in the beginning to think about the problem, like a grand plan. And then take the parts and figure out the parts. So here's what I think the grand plan is. Those will be, I'm splitting into two. I'm splitting this equal the pairs that start with z plus the pairs that end with z. So I'm going to call those pairs z something. I don't know if you guys know this star means anything, z anything. And I put the sizes here. That's the how many. To be technically correct, I'm putting those brackets. That's all the pairs that start with z, and that's the size of how many there are there, plus all the pairs that end with z. Is that correct? Yes. Yes. Is it correct?
You need to subtract the intersection.
I need to subtract the intersection. It's one of these inclusion, exclusion, where when you count this and this, you have to take the common element out. What is the common element? It's only one pair that was in both cases. That would be ZZ. So now, how many are Z and something? 26, because I can put anything in that something. How many are something Z? 26 minus 1, so what's the total? 51. Is there another way to think about this problem? How about, that's correct, I get 51. I'm gonna think about it in a different way. Here's all pairs minus the ones, the invalid ones. As a grand plan of attacking this problem, I'm saying, which ones are all pairs? I already computed that, right? How much is it?
26.
Let's call it star star, right? That's 26 squared. Minus, which ones are invalid pair? How do you get an invalid pair here?
Neither of the two are z.
Okay, so let's call it cross, cross, where the cross belongs to what? Everything but z, right? So it's any pair that's formed with elements, cross say x, xx, or yy, where y is any letter but z, right? That's how I get an invalid pair. I choose anything that's not z. How many of those are there? Choose
25.
anything that's not z times anything that's not z. Is that the product rule?
Yeah.
It's like choosing anything independently of anything and making a pair out of them. But the problem is the choices in here in this product rule are not 26 choices. Are how many choices? Do we follow this? Hands up who's following me, but be honest. So what did I do here? I say, instead of thinking this way, I'm going to think in a different way. I'm going to say, look at all pairs minus the ones that do not contain z. The difference will be the ones that do contain z, right? The ones it's easy, I already got this somewhere here, 26 squared. And now, for the ones that do not contain z, it means I still have a product rule of two initials. Anything that's not z, that's 25 choices. Paired up with anything that's not z, that's 25 choices. This is a product rule because anything goes with anything if the choice itself does not include z. So it's any letter but z. So how many choices are there? 25th squared. 26 squared minus 25th squared? How do you know? Yeah, but how it's, anybody knows the formula for this?
A plus B.
A plus B. There's something else in there? times A minus B. Let's apply this formula. 26 plus 25 times 26 minus 25. This is 1 and this is 51. No calculators needed. All right? So sometimes it's very useful to think of a problem in two ways because that's how you prove things. A problem might be not how many da-da-da, but instead show that this way of thinking is that way of thinking. Show that 26 squared minus 25 squared is 51 or something like this. Counting the same quantity in two different ways. It's a good way to solve combinatorial problems. Could apply to graphs, could apply to logistics, could apply to scheduling. So that's what we did here. We counted exactly the same number of pairs that contain Z in two ways. Part C, how about 3 upper case initials with Z? So that would be, I want 3 uppercase initials, not 2. If I apply inclusion and exclusion, what do I get? I could have Z anything, anything, right? That's anything that starts with Z, plus anything Z anything. That's the triplets that have Z in the middle, plus anything anything Z. That is the triplets that have Z at the end. So now I think I'm in this case here. I counted everything that started with Z, everything that has Z in the middle, and everything that has Z at the end. But obviously, there's a lot of triplets which I counted multiple times, like Z, Z, A. I counted that in here and in here, right? So applying inclusion, exclusion, what do I have to do here? Subtract who? The intersection of those two is what? That's everything that's Z, Z, anything. The intersection of Z, anything, Z, and the intersection of anything, Z, Z. But now, these elements in the middle been added 3 times and subtracted 3 times. So I have to put back the intersection of 3, which is Z, Z, Z. Now, these are all sizes. When I put the straight bars, I mean sizes. And technically, I'm supposed to put those parentheses to indicate sets and the size of the sets, but I'm not being graded by TAs, so I don't lose points if I don't put the curly brackets. I would suggest you do, so you don't lose those points, right? How much is ZZX?
26.
How many things are in this set here?
26.
26. How about this set, ZXX?
26.
26 squared. 26 squared, 26 squared, 26 squared. That's 3 times 26 squared. 26, 26, 26. That's 3 times 26. And this guy is? In many combinatorial problems in this class, unless the problem specifically asks for the total, we're not going to ask you to do the total. Because that's just pure arithmetic, calculate this. If you get this correct, that's pretty much the combinatorial answer. You may need a calculator to actually say, okay, how much is it? Right. So now that I have that one, how about these initials? I have 2 upper initials, like VP, and I have 250 students. Is it guaranteed that at least 2 have same initials? When I say same initials, do I mean in order? Do I mean VP is the same as PV or different ones? So if somebody is VP and another person is PV, do they count as the same initials? No. That's something you have to either know or ask. Do you mean in order or out of order? If it's out of order, PV will be the same as VP. But when people talk about license plates, initials, names, so on and so forth, they mean in order. Otherwise, they will be more specified like sets of things. in order. Can I guarantee that with 250 students, if I look at everybody's initial, there's at least 2 of them with the same initials? There's 250 versus how many pairs of initials are there? We already computed that, right? 26 squared. 26 square pairs. How much is 26 squared?
676.
676. 250 is not enough to guarantee that at least 2 have the same intersection, right? So how about 2,500 students? Now 2 of them certainly will have the same initials because 2,500 students, pigeons, into 676 boxes. But to be more exact, I don't want just 2 of them have the same initials. How many are guaranteed to have the same exact initials? So number of students guaranteed with same exact initials. Isn't that just pigeons into boxes? So how do I do that? 2,500 divided by 676, and I take the round up. So that's 4? Okay. So I have at least 4 students that have exactly the same initials. Same thing I can do for birthdays, right? If I have so many people, so many birthdays possible during the year, right? 365 birthdays. Once I have, 1,500 people, there will be 4 of them with the same birthday. Okay. So that's good. That's kind of a recap of where we were last time, except last time we didn't do those examples. I wanted to kind of pinpoint what's up with product rule, sum rule, inclusion, exclusion if we have intersections, pigeon principle. Permutation rule is something that we've done last time, and that's what we're going to do next right now. But I want to introduce what combination means, and then we'll get back to what we said about permutations. So permutation rule is P of nk choose a sequence of k out of n. For example, when we have natural sequences, if say I go to a restaurant and I want to get a meal of 3 items, I pick 3 items in a certain order to eat them, right? If I want to say I want to organize my schedule for today, I have 25 requests of people wanting to meet with me. I can't meet all 25. I'm going to pick 6 of them to meet today. And I'm going to pick them in an order or out of order when I do my schedule.
In an order.
Clearly the schedule have an order. You mean this person at that time, this person at that time, so on and so forth. What's another example of a natural order where you choose things and the order matters? License plates, right? There's so many letters and numbers to choose from, but the license plates, it's only like, say, 6 characters. You have to choose 6 out of how many, possibilities are there, but in a license plate, the order matters or not? It does. If you take the same letters in a different order, that's a different license plate, right? So clearly when I say sequence, I mean you get to choose k out of n, not k is smaller than n here. It's not all of them. And the order matters. And we're going to call that choice something like with round brackets, say A1, A2, AK. That's a sequence of k things. Combination rule, we're going to call it CNK. I don't like CNK, that's the American notation. I'm going to use this particular notation. It's a big parenthesis with an A up and a K down. That's the European notation. And it says choose a subset of K out of N. So clearly this means in order, and this is a subset, A1, A2, a k out of order. Permutation rule, I want to choose k out of n in a certain order. Combination rule, I want to choose k out of n in any order. What's a natural example of choosing k out of n as a set? Louder, please.
Cards in hand
I can hear you.
and playing cards.
Playing cards. I choose the cards. So the cards, if I choose them as a, what I have in my hand, you know, when you play bridge or whist or that like that, that's a set, right? The cards in my hand. But if I choose how to play the cards one by one, is that something where the order matters or not? When I play the game, does it matter in what order do I play my cards? So when I play the actual cards, the order matters. But when I get the cards and I see them in my hand before playing them, that's just a set of cards. How about if I choose 20 students to come to my birthday party? Is that an in order or out of order thing? It's out of order, right? It's clearly I choose a subset. How about I choose 10 people to make a soccer team? Is that in order or out of order? Out of order. It's choosing a subset, right? How about I choose the courses that I'm going to take, say the next 2 years or the next year. It's choosing 3 or 4 or 5 courses out of, you know, there's like 30. Is that in order or out of order?
In order.
You choose the courses for next year, right? You only have so many, you know, possibilities. There are clearly more courses than you can take. You mean choosing in order or out of order? That you should ask. If you get such a problem in exam, you should definitely know. Because, you know, who knows what the guy who wrote the problem mean? That would be me, right? If you mean in order, it's a different answer than if you mean out of order. You can think of it as what classes I take overall next year, or what's my exact schedule, what class I take in the fall, what class I take in the spring, so on and so forth. And that would be now in order. Right? So in some cases, it's better to either the problem should state very clearly, or you should ask. Right? Typically, when you see things like sequences, they mean in order. When you see things like sets or subsets, they mean out of order. Simply because if I change the order here, I say A2, A3, A1, so on and so forth, that's the same set. When you write these elements, it doesn't matter which order you write them, you get the same set. So what's the relationship between those two things? As a number, right? The permutation rules and the combination rule, they're not giving you the subsets or the sequences. They just tell you how many. It's a number. This n choose k, that's how we're going to call this. N choose k. Both Americans and Europeans call it n choose k, but they write it differently. People in here write it this way, and people in here write it that way. And I think there's another notation, something like CNK.
Yeah.
You can use anything you want as long as it's clear. I prefer this one, n choose k. So those two are numbers, both of them. They say, how many ways can you pick k out of n? Out of order or in order? We already, I think, last time established how much is this number, right? So what did we say? P n choose k is, again, choose k out of n in order. And the way we did it last time was to say, okay, well, you have how many spots in here? How many things you're going to choose? 1, 2, up to? You're going to pick k things, right? Because that's what it says, pick k things. So how many options I have for the first element I'm picking? And I'm literally thinking of now not as mathematics, but as a procedure. If I ask a computer, pick k things in order out of n, what is the computer going to do? Or the machine? It's going to pick the first one, then it's going to pick the second one, then it's going to pick the third one, so on and so forth, right? This is not the product rule. Why? There's some dependency between choices. If I pick this as my first item, I can't choose that item again because these items can only be chosen once, right? So how many options are here? N options. Once I pick the first item, how many options are left for the second spot?
N minus 1.
N minus 1. N minus 2. And well, by the time I get to the kth option, how many options are here?
N plus 1.
How many?
N minus k.
Not exact, right?
Oh, plus 1.
Plus 1 or? How do I check myself to be correct? When I do this thing and I'm not sure, this is an indexing question, right? I do indexing 1, 2, 3, 4, 5, and I want to know after k things, what's my value of that index? At index 1, I have n, minus 0, right? At index 2, I have n minus 1. At index 3, I have n minus 2. At index k, do I have n minus k? Is that how it works? Is it like index n minus the index? No. It's a little one off, right, from the index. So that's how you look at it to say that's how many options you have. Can I multiply those things now? Even though it's not a product rule, because product rule requires no dependencies. Clearly there's a dependency here. If I pick certain 3 items, when I to the 4th spot, I can't pick those items anymore. But it's still a multiplication. So this would be n times n minus 1, n minus 2, up to n minus k plus 1. And we said if you want to see that better, you can multiply all of them, n minus 1, n minus 2, up to n minus k plus 1. But then I can add up to simplify the thing, the next ones, n minus k minus 1, all the way to 2 and 1, and divide by these guys, n minus k minus 1, up to 2 and 1, right? Multiplying with something and divided by that something will give me the same answer. But now I have a concise form of writing the numerator. This will be what? The whole numerator is n factorial, and the denominator is?
N minus 2.
Now I want to think of this in a different way. Instead of asking the computer to do it that way, pick the first one. How many options are there? N. Now that you pick the first one, pick the second one. How many options are there? N minus 1, right? That's what we did on the right side. One by one, pick those choices. On the left side, I want to do it differently. I want to first choose the items as a set, and then permute them. So how does this work? Suppose I'm picking, what did we say makes sense as a natural order? Things to eat in a certain order, like for the meal. I could pick the first one, there's so many possibilities, n, the second one, and third one, that's what we did. Or I could say, I'm choosing as a set the items from the menu I want to eat, and then choose the order of this set. Would that work? Would it give me kind of the same number? So let's write it down. So this is a 2-stage plan. First, choose k items as a set out of n. So out as a set means not in order. And then choose the order. Would that be the same kind of, it's a one-to-one map, that's what I'm implying. If you do it this way, for every result that you get this way, there is a way to do it this left way and get the same result. Okay. Is that true? So those two procedures achieve the same possibilities, the same number of possibilities too, if they're the same possibilities. So one way, choose one item. Now given that, choose the second item, choose the third item. So I'm going to get k items. And the other way is choose a set. So the set might be something like A1, A2, AK. Those are my choices. And then choose an order that is permute this set A1, AK into all possible sequences. So once I choose a set, actually let's do here something easier. A, B, C, 3, K equal 3. And now if I permute this set A, B, C into all possible sequences, what are my mills looking like? A, B, C, that's a sequence. A, C, B, that's another sequence. B, A, C, B, C, A, C, A, B, and C, B, A. So once I pick 3 items, I can make many orders out of those 3 items. So I'm going back to my original question. Is this left way the same as the right way? In other words, for any way somebody chooses a set and then an order that corresponds to the machine in here choosing a first element, a second element, third element, so on and so forth to get the same result? How about the other way? If somebody chooses the items, does that correspond to effectively a set and an order? So what I'm saying here is a one-to-one map. You can do it this way and this way. And for any possibility of a result here, so take for example, say the set is A, B, C, D, E. Suppose one possibility result, somebody's got n equal 5, so k equal 3. Somebody's got here the result D, A, C. On the left side, what that corresponds to, the first choice was D, the second choice was A, and the third choice was C. What is the corresponding result in here? This is a two-stage procedure. So that corresponds to what? The first choice was the set of chosen 3 things was A, D, C, because 3 things, these are out of order. And then the order was D, A, C. What if this result in here is A, C, D? That corresponds to the same set, right? But a different order. What if the result in here is B, C, D? That corresponds to a different set, the set of B, C, and D. So we said everything we can get in here, we can also get on this side. How about the other way? If somebody chooses a set and an order, automatically can I replicate this result in here by making the right choices? I would like you guys to think about this. This is a fundamental counting mechanism where I have some things I want to count and I think about that in 2 different ways. It's going to happen a lot. Most of the time it happens because we want to count something and we don't know how, but then thinking about it in a different way, we know how. But it could happen that simply we want to prove that this way is equal to that way, and the way to prove that is to just count it in 2 different ways. So if this is true, what is, so on the left side we already found this number, right? On the right side. What is on the left side? How many ways can I choose k items out of n? Out of order. This way. Right? By definition. So this is the definition of n choose k. Choosing k items out of n, out of order. And how many ways can I choose the order of k things? Now I have k things. How many possible ordering of those k things are there? Yes? K factorial. You guys look stunned. Is anything stunning happening here? So what did we do here? We say we want to count how many ways can you choose k out of n in order. That would be, say, the schedule for today. I want to have 6 meetings out of possible 25 meetings in a certain order. One way to do that is to choose the first meeting, choose the second meeting, choose the third meeting, up to the kth meeting. And that's how many ways I can arrange my meetings. A different way to do that is to choose first the 6 meetings that I want to have today out of order as a subset. And then once I have those 6 meetings, just choose a particular order of them. This is the number of choices for 6 meetings. And this is in how many ways I can order those 6 meetings today. And the result between those two is what? Is a product. Can any choice of k go to any ordering of k? Anyway, I choose my 6 meetings, I can organize them in any particular order of 6 factorial permutations. So this in here is n choose k times k factorial. So what did we do? We showed that this is equal with that, because they count the same thing in 2 different ways. That was actually my plan from the very beginning. My plan in here, the reason I'm counting this in 2 different ways is because I want to end up with a formula for n choose k. Because that's, I know n choose k means choose k out of n, but I don't know what is that number. Now that I have this, n choose k times k factorial is n factorial times divided by n minus k factorial. Then can I get n choose k out of there? I get n factorial divided by n k factorial, n minus k factorial, which is the formula for n choose k. Now, I think in the regular section, the proof of this is not required. The regular section, just get n choose k, here's the formula, apply it. You want to see if they didn't improve, ask them why is this. You should know why this is. It is because I'm counting this in 2 different ways. Right side gives me this, this way. And left side gives me n choose k times k factorial. They have to be the same thing. Therefore, I can extract how much n choose k is out of here.
Okay, so I'm not sure I'm fully understanding. So when you have like the set A, B, C, right? Let's say that's some subset of length k, right?
Right. So the subset might be A, B, C, D, E.
It could be anything, right? But we say it has length k. So for that subset of length k, we're saying that it's always going to have k factorial different ways to arrange them, right?
Right.
So when I'm thinking, oh, all these possibilities, right? You're saying that we have to divide out k factorial because that gets rid of the repeats.
You can think about it that way. That's not what I said, but that's a valid way of thinking about it. He's saying a little back. He's thinking a little backwards. He's saying, if that's how many ways is to get k sequences, the way I can extract the sets out of here is to say every single set has been enumerated k factorial times. Because every particular set like DAC as a sequence show up 6 times. DAC, DCA, ADC, ACD, so on and so forth. So if I divide with k factorial, I'm getting just the sets without order.
Yeah, I'm not following how those do the same thing.
So in your thinking, he's saying enumerate all the sequences of k out of n, like DAC, ACD, right? There'll be 6 of them. If I want the set, not the sequence, I have to take all these sequences and divide by k factorial because every set appears k factorial times in here in different order. So the reason, in your way of thinking is to say, if I take all the sequence, I list all of them. There'll be a lot of them, right? If I divide by k factorial, I get the number of sets. That's not what I said. What I said is there are 2 different procedures for generating all those sequences. One is choose element by element all of them. If I do that, I get this value. Another way to generate all the sequences, different way, completely different way, is to generate all the sets first and then permute all those sets into sequences. Because every set will give me k factorial sequences. So now if I multiply the number of choices for sets with the number of ways I can permute each set, I'm going to get all the sequences. Hands up who's with me here. This is definitely something, it's very easy to remember this formula. I'm sure most of you knew it already, but how many of you knew why it is true? Right? So this is something you need to sleep on. Not just, clearly we know how to compute n factorials, k factorials. If I tell you choose, 3 things out of 5. 5 factorial divided by 3 factorial times 2 factorial, right? Everybody will be able to do that calculation. I want you to know why is it true, which has to do in how many ways can I permute the k elements and n minus k elements and so on and so forth. All right, so now we have permutation rule in how many ways can I permute k out of n elements, and combination rule, which is in how many ways can I choose k out of n elements. And the relationship, I'm going to state it again, between them is that this times k factorial is p of nk. Because for every set of k, I can permute it in k factorial way to get a sequence of k things. Also, at this point here, n choose k is number of subsets of size k. That's nothing to think about. It's just a way of rephrasing what combination means. When I say choose k out of n, I mean choose a subset of k. So how many ways to choose k means how many subsets of size k are there. Right? Because that's not a thinking or inference or logic. Just rephrasing the definition. Choose a subset. If there's so many ways to choose a subset, it's got to be that there's so many subsets. So who's then n choose 0 by this way of going about? Yes. Number of subsets?
It would be the number of subsets of size 0.
Okay. Number of subsets of size 0. Well, how many subsets have size 0? 1. How about n choose 1? Is the number of subsets of size? How many subsets have size 1 if I have n items? How can I make a subset of size 1? I have to choose one of them, right? How many ways are there to choose one? How many subsets of size n? Which one? All of them. How about n choose 2? Subsets of size 2. Is this in order or out of order? When I say subsets of size 2, is the subset AB the same as subset BA?
Yeah.
Yes. So how many subsets of size 2 are there?
N squared minus 2n over 2.
What is it? N squared?
Minus 2n.
Like that?
Yeah, over 2.
Why?
Sorry, just not 2.
Minus n then? Why is that?
Just n times n minus 1 over 2.
No, but why?
Because n divided by n minus 2 factorial removes all the elements except for the n minus 1.
That's a complicated answer. Right. Is this the correct number? Anybody remembers the formula? Like the number of way of choosing 2 out of n is n times n minus 1 by 2. So can I think in terms of pairs? I want to go back to what he said. How many pairs are there if I choose the first element? I have to choose 2 things, right? Choose the first one. How many options are there? N. Choose the second one. How many options are there? So if I choose the pairs in order, aka AB, which is not the same as BA, I get n times n minus 1, right? Because you have to choose one, and then you have to choose the other. That is exactly P of n choose 2, right? Take 2 in order. The problem is, as sets, as pairs, that's all okay, that's a correct answer. But as sets, everything here is counted twice. Every single set, like AB, has been counted as AB and as BA. Right? So I have to take this number, divide by 2 to get it out of order. That's because 2 factorial is 2. So when I divide it here with k factorial, that's what happened. But 2 factorial happened to be 2. What happens if I apply the formula directly? So n choose 2, just apply the formula. N factorial divided by this formula right here. 2 factorial, n minus 2 factorial, right? What's the easy way to think about this? N factorial contains all the n minus 2 factorial and 2 more factors, which are n times n minus 1 divided by 2 factorial, but 2 factorial is 1 times 2, so that is 2. So for every one of these problems, at least for the first week, that is from today to next week, please don't apply the formula like a robot mechanically. Oh, you give me k equal 2 and n equal 5, I can plug these numbers and get the answers. If you want to learn how this works, you have to think about it in a combinatorial way, in a counting way. Okay, so we established this. This is a very important thing. Let's go quickly through some examples here. Examples. I mean, we do that one, n choose 2. 10 packages, 6 heavy, 4 light. Select 5 of them. When I say that, I mean irrespective to heavy or light. How many ways can I choose 5 packages? Is that in order or out of order? When I say choose 5 packages out of the 10 to deliver. So what is the answer?
10 times 9 times 8 times
10 choose 5. So when in combinatorics, we could do 10 factorial divided by 5 factorial times 5 factorial, and we can compute this value, but the answer I care about is this. The conceptual, if you want to choose 5 out of 10, is this 10 choose 5. How about select 3 heavy and 2 light? I want to deliver 5, but not any 5. 3 heavy and 2 light. How can I do that? So I have 6 heavy and 4 light. I want to choose 3 heavy and 2 light. How can I do it? Yes.
6 choose 3 plus 4 choose 3.
Yes. It's times. Is that a product rule in there? Any way you choose 3 out of the 6 goes to any way you choose 2 out of 4. There's no restriction, no dependencies. So that's a product rule. This is like so many choices to choose the heavy ones and so many choices to choose the light ones. Since every choice goes with any other choice, it's like choosing jackets and pants. If everything goes together, that's how many ways I can make the choice. Product rule means there's no dependency between the choices. Any choice you make here, any choice you make here goes together. How about how many bytes, that is 8 bits have exactly 3 ones. When I mean a byte is 8 bits, I mean in order or out of order. A byte is a set of 8 bits or a sequence of 8 bits?
Sequence.
It's a sequence. When you think of a byte, clearly you're not just thinking of I have 2 ones and 6 zeros or 5 ones and 3 zeros. You clearly mean the byte has an order, right? Computers definitely use the order to represent those numbers. We've seen in binary 1101 has 3 ones, but if I change those ones, I get a different number, right? So that's clearly a sequence. How many of these sequences have exactly 3 ones? Meaning the other 5 are zeros, right? Because in binary there's only 1 and 0. If there's 3 ones, the other 5 has to be zeros. How many of those sequences have exactly 3 ones? A choose 3. How come it's A choose 3 if this is a sequence? What are the items that I'm choosing 3 out of 8? What are those exact items? Yes?
You're choosing a specific digit to
Spot.
be a 1. Yeah, spot.
I'm choosing 3 spots out of how many spots? 8. Are those choices of the 3 spots in order or out of order? So I choose this spot, and this spot, and this spot. So the spot, this spot is spot 1, 2, 3, spot 4, and spot 5. So I'm choosing this spot here, and this spot here to put my 3 ones. Is this choice, the choice itself, in order or out of order?
Out of order.
It's out of order because if somebody chooses spots, what did I say? 3, this is 3, 5, and 6, right? Spots 3, 5, and 6 are the same as the spots 6, 3, and 5, right? If somebody chooses these spots instead of these spots, you get exactly the same sequence with the ones in position 6, 3, and 5. So while the problem setup refers to a sequence, the choice itself, I'm choosing 3 spots to put the ones, it's out of order because I'm choosing a set of 3, not a sequence of 3. That's why it's A choose 3. Here's an exercise, I should say clearly honors exercise. How many 8 bits sequences, that's a byte, have not 2 consecutive ones? So in other words, I want the sequences that don't have ones next to each other. I'm not going to do that. You have to think about that. So I want to know how many bytes don't have 2 ones next to each other. Here's another thing. We were doing here n choose 2, number of subsets of size 2. But whose n choose n minus 2? Number of subsets of size n minus 2. So how much is that? If I apply the formula, what do I get? N factorial. Who's my k factorial here?
N minus 2.
N minus 2 factorial. And who is n minus k factorial? 2 factorial. Isn't that the same? Is there a combinatorial explanation for why this is the same as that? Yes.
It's because when you choose 2 elements, or choose all but 2 elements, either way you're still choosing 2 elements to include or exclude.
If I want to choose 2 students to send outside, I can choose those 2 to send out, or equivalently, I can choose the n minus 2 who stay in. is a choice that results in the same exact, is back to counting the same thing in two different ways. I can either count the possibilities of sending 2 people out, or count the possibilities of n minus 2 people remaining in. Those are subsets, right? Either way, I'm getting the same number of possibilities. So in general, n choose k is the same as n choose n minus k. Because I can choose the k to take or the n minus k to remain. And that's the same choice effect. And another interesting fact about combinatorics, who is then n0? We say that's a number of subsets of size 0. Who's n1? Number of subsets size 1. N2, subsets of size 2. And n minus 1, we say that is subsets of size n minus 1. And the last one is subsets of size n. Now, I think this is a sum rule. If I look at all my subsets, all of them, each subset has a size, right? And some subsets fit in here, some subsets fit in here, some subsets fit in here, so on and so forth. Isn't that all the subsets of a set? Isn't that the power set? Is it a sum rule, or do I have to worry about intersections like in inclusion, exclusion? Is there any set that will be in multiple categories in here? Like a set of size, yes?
No.
No.
Because since they're all different sizes, like it's impossible that one of the other things will have the same size set.
Correct. So if somebody has size 3, it can't possibly have size 7 at the same time, right? So there's no intersection, therefore it's a simple sum rule. Take all the sizes of size 0, size 1, size 2, size 3, that's all the subsets. So if I add up all this, this is the size of the power set. Right? Because it's all subsets from the power set. How much is it?
2 to the n.
2 to the n. So these numbers, n choose k, have this property that if you sum up all of them with a fixed n from 0 to n, I could write this up a sum, right? Sum from k equals 0 to n of n choose k. That's the same sum as on the left side. How about if I alternate the signs? So I say n choose 0 minus n choose 1 plus n choose 2 minus n choose 3, so on and so forth. The last one is going to be minus 1 at some power n of n choose n. By alternating the sign, plus minus plus minus. What is this?
Is it 0?
I don't know. Maybe 0. But why 0? Is there a combinatorial way to think about this?
Because the last ones are equivalent to the first ones, so they cancel each other out.
I think he's looking into that formula we had here, this, right? He's saying maybe this one cancels with that one because they're the same. Hopefully one is plus and the other one is minus, right? To cancel out. So let's see if that works out. If n equals 5, what is this relation saying? 5 choose 0 minus 5 choose 1 plus 5 choose 2 minus 5 choose 3, right? Plus 5 choose 4 minus 5 choose 5. Would these guys cancel out somehow? Let's see. 5 choose 0 should cancel out 5 choose 5 because k is 0 and minus k is 5, right? So that goes away with this. 4 goes away with 1. If k is 1, n minus k is 4, right? Because n is equal 5. So this guy here goes away with this guy here, and those two follow the k and n minus k. If k is 2, n minus k is 3, right? So these guys go together. So I get 0. Very good. That's if n is odd. Because you can see when n is odd, it's exactly that pairing that this guy goes nice with that guy. So I'm using the formula that n choose k is n choose n minus k here. For various k's. For k equals 0, n minus k is 5. For k equal 1, n minus k is 4. For k equal 2, n minus k is 3. This guy cancel out. Fine. What happens if n is equal 6? You have a question?
No, I can say what happens.
You know what happens?
Yeah.
Let's write it down and then you tell us what happens. 5 choose 0, 6, sorry. Minus 6 choose 1, plus 6 choose 2, minus 6 choose 3, plus 6 choose 4, minus 6 choose 5, plus 6 choose 6, right? Is that correct? Now, the problem in here is that how many terms I have? From 0 to 6, including 0, including 6. How many terms is that? 7. That's an odd number. I can't hope to cancel an odd number one by one because canceling goes in pair, right? If I use this formula, something has to go away with something. That's a pair, but I have 7 things to cancel out. 7 things cannot be canceled out 2 by 2 by 2 by 2. Is this still 0 or not 0? Not 0. Can anybody calculate? How much is 6 choose 0?
1.
6 choose 1? Choose 2? N times n minus 1 by 2, right? How much is it? 6 times?
15.
15? 6 times 5 divided by 2? How about 6 choose 3? That's a toughy one. Let's do 6 choose 4. That's the same as 6 choose 2, right? So that's 15. 6 choose 5 is the same as 6 choose 1. And 6 choose 6 is only 1, right? So 6 choose 3, I think we have to apply the formula here. 6 factorial divided by 3 factorial, 3 factorial. That is 4 times 5 times 6. I'm removing a 3 factorial to start with from 6 factorial. So I kind of cancel one of the factorials. I still have 3 factorials. How much is 3 factorial? 4 times 5 times 6 divided by 6. So now 1 minus 6 plus 15 minus 20 plus 15 minus 6 plus 1. Can anybody do this calculation? 1 minus 6 minus 5
It's 0.
plus 15, 10. Minus 10,
Minus 20.
minus 20,
Negative 10.
minus 10, plus 15,
Plus 5.
plus 5, minus 6, minus 1 plus 1. Still works out, they think.
It's not a coincidence that that's a row of Pascal's triangle, right?
No, it's not. How would you feel if a professor comes in class and say random things on the board? Of course, it's not a coincidence. So how does this stuff works? Yes.
So choosing one thing from a group of 6 is the same thing as choosing 5 to exclude from a group of 6. So that's why they're the same.
Yeah, but I think we established that works clean thinking in a odd case, because in an odd case, clearly n choose k goes away with n choose n minus k, which we established the same quantity, and they will have different signs. The plus and the minus will be on different spots. But how does this work? I want to show you the general principle. That's again, it's another thing, like the other sections won't do. What I do is here. So the real principle is called binomial expansion. Or theorem. That says, what happens when I do x plus y at power n? How does that work? Well, let's see. X plus y times x plus y, everybody knows that is x squared plus 2xy plus y squared, right? That is 2 choose 2 x to the 2 y to the 0 plus 2 choose 1 x to the 1 y to the 1 plus 2 choose 2 x to the 0 y to the 2. I'm writing it that way so you can see what's happening. How about x plus y cubed? Well, that is x plus y squared, which I already computed, times x plus y. So if you do the calculations, you're going to get x cubed plus
X squared divided by
3 x squared y plus
3
So I can write that as 3 choose 0 x cubed plus 3 choose 1 x1 y x2
You choose 1 x squared.
well, let's start with 3 then. 3, 2 x squared y1 plus 3 choose 1 x y squared plus 3 choose 0 x to the 0 y cubed. And you can imagine what's going to happen if I do without expansion. What am I doing happen to the fourth? I'm going to have 4 choose 4 x to the 4 y to the 0. There's a y to the 0 here, which of course is 1. Plus 4 choose 3 plus 4 choose 2 plus 4 choose 1 plus 4 choose 0 x0 y to the 4. So what she was mentioning, Pascal triangle, has to do with exactly this. 1, in here we have 1, 2, 1, that's this row. In here we have 1, 3, 3, 1. In here we have 1, 4, 6, 4, 1. If you look at those coefficients, this is a 1, this is a 4, that's a 6, that's a 4, that's a 1. This one's here is a 1, 3, 3, 1. So this is what Pascal triangle is. Can anybody tell me the next row? You have to know it from before to know what the next row in the Pascal triangle is. Yes. Hold on, let me put the next row and I'll answer your question.
It's 1, 5, 10, 10, 5.
1, 5,
10, 10, 5.
What's the question?
For the 4, choose 1. Should be y to the 3.
This one?
Yeah.
Y to the
3.
3, right? That's what you mean? Correct. So how did you guys get this new row here? Where's the 5 coming from?
1 plus 4.
1 plus 4. Where is the 10 coming from? 6 plus 4, 10. 4 plus 1, 5, so on and so forth, right? Is there a general rule that dictates this? Because these are all combination values. N plus 1, the next row, choose k, is n choose k plus n choose k minus 1, something like that? That is, how do I get an element on the next row from the elements of the previous row? This is row n, and this is row n plus 1. Right? That's the rule that's being applied to generate the next row in Pascal triangle. I'm just 1 becomes a 1, and then the next 2 gets added 5, 10, so on and so forth. Can anybody explain this to me with combinatorics? I mean, I can plug in n factorial, k factorial, n minus k factorial, and verify that's true algebraically, right? I can take this formula from here, what is it? The factorials, and plug it in. There is a combinatorial explanation for why this is true. What is that? Remember in the beginning, the first week or 10 days or 2 weeks, we don't want to use the factorial in an algebraic way. Clearly, what this is saying is n plus 1 factorial divided by k factorial times n plus 1 minus k factorial is n factorial divided by k factorial n minus k factorial plus n factorial divided by k minus 1 factorial times n minus k plus 1 factorial. That's what it means if I replace everything with factorials. But I want an explanation for why this is true in a counting way. Yes.
N choose k is all the subsets of k if your set is size n. And then n choose k minus 1 is all the sets that are 1 less than that. And then if you add 1 to your overall set, you can just add that element of that set that you just added to all the n choose k minus 1 subset.
How many people follow that? I think you might be right. Here's a simple explanation. I want to choose k out of n plus 1, right? So I'm looking at this n plus 1 and I say, here's the elements, x1, x2, xn plus 1. Those are all the choices I have. I want to choose k out of them. I have two possibilities. Remember, when you think of counting, first make a grand plan. That's the plan to attack the problem. What's the main principle how this problem works? Like all the plates minus the invalid ones. That's the plan. Here's my plan. All the subsets I can generate, I'm looking at this guy here. Out of two, I'm going to apply the sum rule. I'm going to split them into two disjoint possibilities. One that contain this element, all the subsets of size k that contain the last value, and all the subsets of size k that do not contain the last value. Is that all possibilities? Any set can either contain that or not contain that. Do I have empty intersection in between? Can I have a subset that contains this one and the same times do not contain xn plus 1? No. So those are the sum rule, right? So I can sum up how many of these sets contain the last element and how many of these sets do not contain the last element. But how many do not contain the last element? How do I make subsets of size k excluding this guy? I have to choose subsets of size k from here. How many subsets of size k I get without the last guy? That's right here. You got to choose k out of n. And now if I choose the last element, since I want to make a subset of size k, how many I have to choose from the rest?
K minus 1.
That's right here. Out of the remaining n, choose k minus 1. So this is a sum rule that says if you want to choose k out of n plus 1, you can think about that in two ways. Either choose the last one or don't choose the last one. If you don't choose the last one, you have to choose all k out of the first n. If you choose the last one, that's 1 of the k. The other k minus 1 have to be chosen from the first n. And since this is a sum rule, because there's no intersection, I don't generate the same subset twice, I can just add them up. Again, you guys look stunned. I think it's essential in the first week or two of combinatorics to think in a counting way, not in an algebraic, here's the formula applied, k factorial, so on and so forth. Okay, let's go back to this thing. Here's what I'm going to say. This is a sum from k equal n down to 0 of n choose k, x to the k, 1, a to the minus k. That's a general formula that happened here, and here, and here, so on and so forth, and it will keep happening. How can I prove this thing? If I have x plus y times x plus y times x plus y times x plus y times x plus y, and n factors, parentheses, right? So this is the first one, second, nth. That's what x plus y power n is. It's the first parenthesis times the second parenthesis, third parenthesis, so on and so forth. When you know how you open parentheses up? You multiply everybody with everybody, right? So how do you open parentheses? If you have something like x plus y, you multiply, you pick somebody from the first parenthesis to multiply with somebody from the second parenthesis. And if it's x times x, you get x squared. If it's xy, you get xy, then yx, that's another xy, and then y times y, it's y squared, right? In here, this is effectively x plus y times x plus y times x plus y, 3 times. How do I get, how many terms are effectively here without the grouping? Count this as 3x squared y. This is x squared y plus x squared y plus x squared y. This guy here. There are 8 terms here, right? 1, 3, 3, 1, 8 terms. Those 8 terms come from picking something from the first pair, times something from the second pair, times something from the third pair. For example, x times x times x. Or x times y. This x times this y times this x will give me x squared y. But so will be x times y will give me another x squared y. And so on and so forth. So if I think in general, I pick this term, xk, yn minus k. How many of those do I get? When I open all parentheses, how many times I'm going to get x times x times x, k times, and y times 1 times y, and minus k times? First of all, when I open parentheses, how many terms are going to be there before the grouping? If I have to pick something from here, times something from here, times something from here, times something from here.
You get 2 to the end.
2 to the end. Because there's 2 choices here, x or y, 2 choices here, x or y, 2 choices here, x or y. So there's 2 to the end total number of terms. But some of them, they look the same. Like this x squared y came up 3 times because it comes from x times y. It comes again from x times y times x. And it comes again from y times x times x. Those 3 factors, when I multiply them, they all give me x squared y. All that's left is to say how many of these x squared y's I get. So when I this is a general question. How many x, k, and then minus k? I have to make a choice in each parenthesis, right? Whether I pick the x or the y to multiply. This means what? This corresponds to how do I get exactly x at k and y at minus k and not x at some other power times y at some other power? Somebody else. We are way into the honors realm here. But that's okay. Yes?
Because for every x that x chooses to be multiplied with, it chooses to not be multiplied with by a y. So we have to
So every one of these products comes from choosing something from here, times something from here, times something from here. Of course, I can choose y, and that will result in what? Y to the n. If I choose x, will result to what? X to the n. The reason those are only one of those, x to the n, is because there's only one way to choose x. That's only one choice. But if I want x at power k times 1 of n minus k power, it means I chose in how many parentheses I chose the x? K. And in how many, the rest of the parentheses, I chose the y. Right? So that means in k parentheses, choose the x. In the remaining n minus k parentheses, choose the y. How many ways can I do that? In how many ways can I choose k parentheses here to pick the x out of them? That's n choose k. So that's why the coefficient of this term, meaning the grouping, how many times this term is going to show up in the expansion, is exactly n choose k. So if you look at x squared y, how many of those terms I had here? 3. That's exactly 3 choose 1. If you look at x y squared, that's 3, is 3 choose 2. So this is the binomial theorem, and that works for any x and y. Notice that x and y here are just symbols. I can plug any numbers I want into x and y. So how can I prove this? Can I plug some x and y to make this work? Somebody else. If I say x plus y at power 6, 6 is the power here. That will be the sum from k equals 6 to 0 of 6 choose k, x to the 6, y to the 6 minus k, 6 minus k, right? Can I plug an x and y to get exactly this formula? Well, the 6 choose k are already here. So all I need x and y is to control the sign. So what x and y do I need to get exactly this? Yes?
Plus 1 minus 1.
Right. If I plug in plus 1 and minus 1 in here, I get exactly this formula. But on the left side, what happens to plus 1 and minus 1? I get a 0. So that's how I can prove this. I use the binomial expansion with x equal 1 and y equal minus 1. All right. We're going to have to continue this on Friday.
How'd you feel about the honors realm? Bro, I was like dozing off in the beginning. Bro. I'm being enlightened. I like the enlightenment. No, I mean, yeah. Do I need to understand it or keep it in my head? No.
Is it how many stuff like yeah, the order doesn't matter. Yeah, order doesn't matter. So basically, this is